In this tutorial, I'm going to show you how to install and compile the code in Xcompact3d, and we'll do a brief check that it is running fine. So the first thing I'm going to do is I'm going to create a tutorial directory, and I'm just going to git clone the code directly. Then once we are compiling it, I will go through the parameters of my workstation and few important information about the Makefile. So git clone went successfully. Now I'm going in the Xcompact3d directory, and I'm just going to do a make clean for sanity, and I'm running the make. So you can see the code is compiling the latest version, master branch version of the code. While the compilation is happening, I'm just going to show you that I'm using the GNU Fortran compiler 11.2. I am using Ubuntu 22.04. In terms of MPI library, I am using the OpenMPI 4.10 library. And for the CMake, I'm just going to show you that I'm using the version 3.18.4. So we're just going to check, but the compilation is going well. It's taking a few minutes. While the compilation is going, I'm going to go through quickly with through the Makefile. There are only 3 preprocessing options. By default, double precision is activated to run the simulation in double precision. There is also the option to remove this option to do everything in single precision, or to use this save single option, which means you run your simulation in double precision and you save in single precision. And there is also a debugging mode that will print a lot of information if you are developing into the code. These are the CMP settings. So we've tried a few compiler, Intel, GCC, the Cray compiler, the NAG compiler. We didn't encounter any issues. One thing that might be of interest for you is the fast Fourier transform settings. So by default, the code is using a generic FFT engine, which means you don't have to rely on external library. But if you want to play around with this, you can of course plug different FFT library engine, most famous one being the MKL from Intel or FFTW3. You just need to specify where those libraries are installed, and that's pretty much it. And of course, there's a FFT flag, which you can switch from generic to whatever library you want to use. I want to make clear that we are only doing 2 FFTs per time step. So the performance improvement will be minimal, maybe 5-10% at best. But if this is of interest, you can of course switch. But by default, you can run and compile the code without any external library. You only need a Fortran compiler and MPI library. Right, so we are getting close to the end of the compilation, and at the same time I'm going to prepare, we are going to compile the code with CMake. So I'm just going to create a build directory, and I'm going to prepare the CMake compilation. That will be exactly the same with the same Fortran 11.2 compiler, and right, the compilation with Make is finished. So for sanity, I'm just going to go in the examples directory. I'm going to go in the Taylor Green. I'm going to load the reference test case, which is a DNS, direct numerical simulation of the Taylor Green case at Reynolds 1600. So I'm going to use this one as my input file, and then I'm just going to run the first few iteration using 8 CPU core, and you can see that the code is running absolutely fine. And you can also see that for this test case, you just need to run it for less than 10 minutes, and you will get your first turbulent simulation done. I'm also going to go in the cylinder directory just for sanity. I'm going to take the input for the moving cylinder, input.i3d, and I'm going to use exactly the same command line to run the code. You can see the code is running. It's probably going to take around 1.5 hours to run this test case, which is slightly more demanding in terms of mesh node, actually 1 hour 8 minutes. So you can see once the code is compiled, you can test different flow configuration. For completeness, I'm also going to compile the code with the CMake. So now I've initiated the CMake. I'm just going to use 8 cores to do the Makefile as well, and you can see the CMake is going much faster. You have an indication of where you are in the compilation. So you will generate a new executable, which should be similar to the other one, but this one will be in the build/bin directory. And for sanity as well, I will run the first few time step of the Taylor Green case. So we just need to wait for the CMake compilation to finish, and then we will be done with this tutorial. You can see there are a few warnings during compilation, nothing of concern. This is something that we are going to try to fix in the future, but this will not prevent you from running the code. So we are at 80% now. It should not take long to finish. 90%. And so what I'm going to do, once the compilation is finished, I'm going to go back to the cylinder examples, but I'm going to run the code from the new executable. So as you can see, it's pretty straightforward to git clone the code, to compile the code. It does not rely on external library. It's very straightforward. The Makefile is as simple as it can be. If you are using OpenMP and a GNU compiler on your workstation, you probably have no change to make to the Makefile or to the CMake. So now I'm not going to, just going to use the new executable. It's going to be exactly the same. Right. So you can see you can either use the Makefile, you can either use CMake capabilities. At the end, compilation time slightly faster with the CMake. You don't have to worry about anything. So totally up to you, but you can see that compilation of Xcompact3d is very straightforward.